Welcome to The Explainer. You ever wonder how your email just knows what's junk? Or how a streaming service recommends the absolute perfect movie for you? Well, today we're going to pull back the curtain on the logic that makes all that happen. We're diving into something called classification algorithms, basically the different ways we teach computers to look at the world and make a pretty good guess about what's what. So, to really get our heads around this, let's start with a problem that's, well, a little high stakes. Imagine you're a computer program and you're looking at this mushroom. The question is simple: edible or poisonous? You can't taste it, you can't smell it. All you can do is look at its features. So, how do you build a system to make the right call every single time? That right there, that's the core challenge of classification. Okay, so our first method for tackling this is what I like to call the flowchart detective. This one is super methodical, totally logical. It solves the case by asking a series of simple questions, following the clues one step at a time. And this detective's real name? The decision tree. So what exactly is a decision tree? Well, at its heart, it's basically a model that takes a whole bunch of messy, complicated data and breaks it down into smaller, much more manageable groups. By asking a series of simple yes or no questions about the data, it ends up creating a set of clean, easy-to-understand rules that lead straight to a final decision.
Now, the strategy behind building this tree is a process called recursive partitioning. I know, it sounds super technical, but it's actually a really simple idea. You just split the data, then you split the groups you just made, and you just keep on splitting over and over. And the goal with every single split is to make the new groups as pure as possible, meaning ideally each group only has items of one single type in it. Let's actually see this in action. Imagine all our data is this collection of stick figures. Some are a yes, some are a no. We need to figure out the best first question to ask to divide them up. And it turns out the most informative first split we can make is based on their body shape. So let's do it. We put all the rectangular bodies over here and all the oval bodies go over there. But you can see the groups still aren't totally pure, right? They're still mixed. So we go to the next step. We take each of those two piles and we split them again. But this time, we'll do it by head shape. And look at that. What we get is 4 distinct, perfectly pure groups. Inside each one, every single stick figure is exactly the same. They're perfectly classified.
And what we're left with is this crystal clear set of rules. If a figure has a square head and a rectangular body, it's a yes. If it has a round head and a rectangular body, then it's a no. It's just a simple but really powerful flowchart that any computer or, hey, even a person can follow to make a prediction. All right, let's meet our second thinker. This one is less of a detective and, more of a probabilistic profiler. It doesn't really care about rigid rules. Instead, this character plays the odds, constantly updating what it believes as new evidence comes in. And this is the logic behind the naive Bayes classifier.
So this method asks a totally different kind of question. Instead of following the strict flowchart that spits out a definite yes or no, what if we just calculated the probability of something? What are the odds that an item belongs to a certain class, based on all the features that we can see?
And that question brings us right to the core of the naive Bayes classifier. It uses something called Bayes' theorem, which is just a classic rule of probability, to update how likely an outcome is as new information rolls in. Now, it makes one big, naive assumption that all the features are completely independent of one another. And while that really simplifies the math, the surprising thing is it still works incredibly well out in the real world. Let's make this real with a classic spam filter example. Check out this table. It shows how often the word win shows up in spam emails compared to normal, non-spam emails. And the difference is pretty striking, right? The word win is in 4 out of 25 spam emails, but only 1 out of 75 normal ones. That's a really powerful piece of evidence.
So, before we even look inside an email, what are the odds that it's spam? Well, based on our sample data here, the baseline probability, what we call the prior, is just 25%. So, to start, we assume 1 in 4 emails is spam.
But then we open the email and we see the word win. This is our new evidence. Using Bayes' theorem, we update our belief, and suddenly the probability that this email is spam absolutely skyrockets to 80%. Just that one single word completely flipped the odds. That is the power of probabilistic thinking. Okay, on to our final thinker. This one doesn't mess with flowcharts or complicated probability calculations. Nope, it operates on a simple, really intuitive social principle to figure out where new things belong. So, let's meet the social networker, also known as K-nearest neighbors.
The entire philosophy of the K-nearest neighbors algorithm, we just call it KNN, can be summed up in this one phrase: you are the company you keep. It works on the very simple idea that things are probably similar to whatever is closest to them. You know, birds of a feather flock together.
So how does it work? It's actually beautifully simple. To classify a new, unknown thing, the algorithm just looks at the K most similar things it already knows about from the existing data, and then it just takes a vote. Whatever class the majority of its neighbors belong to, well, that's the class our new point gets assigned. Simple as that. Now, here's what's so interesting about this approach. The choice of K, that is, the number of neighbors you decide to listen to, matters a lot. Take a look at this new client, the purple dot. If we only look at its single closest neighbor, so K equals 1, well, that neighbor is a write-off. So our new client gets labeled a write-off. But if we expand our circle to the 3 closest neighbors, so K equals 3, now 2 of them are non-write-offs. The majority vote flips, and so does our entire prediction. So there you have it. We've met the rule follower, the odds maker, and the social networker. 3 totally different ways of thinking, 3 fundamentally different logics, all of them sharing one single goal: to make an accurate prediction. Let's just put them all side by side for a second. Our flowchart detective, the decision tree, uses a rigid rules-based logic. Our probabilistic profiler, naive Bayes, uses the flexible logic of probability and odds. And our social networker, KNN, relies on the simple, intuitive logic of similarity and just being close by. 3 different paths, all leading to the same destination. So here's the crucial takeaway. These aren't just abstract ideas in a textbook. Right now, as you're watching this, versions of these very algorithms are humming away behind the scenes. They are filtering your email, they're recommending your music, they're deciding which news articles pop into your feed. So the question isn't just how they think, but where they're thinking and why. Something to ponder.